Lesson 29 is Newton's law of universal gravitation. It's a big one. It's a big one. Why is it a big one? It's a big one because Newton wanted to come up with a law or a mathematical relationship that would describe the gravitational force of any two objects, or three or four or multiple objects, in the entire universe. So he wanted a formula that would work for everything in the universe, whether that be an apple sitting next to a pear, or Mars acting on Jupiter, or the moon acting on the Earth, or our galaxy acting on another galaxy, the gravitational forces between them. So something, a formula that will works for everything, which is, as you can imagine, a monumental task. Okay, now Newton um, came up with two relationships that he knew were true. And those are the following. One, he said that the force of gravity, or due to gravity, between two objects is proportional to the product, oops, to the product of the two masses. In other words, if you multiply the two masses together, you'll get the force of gravity. You'll get a relationship with the force of gravity. Okay, and here it is right here. The force of gravity is directly proportional to the product of the masses. Therefore, if I, let's say, double one mass, then it means I doubled the force of gravity between them. If I have one mass, then I have halved the force of gravity between them. So it's a direct relationship, fairly straightforward. The second relationship is that the force of gravity is inversely proportional to the distance, or to the distance squared between the two masses. And we discussed this relationship in the previous section. And again, it's a very important relationship. It's a squared relationship, an inverse squared. Okay, so in this relationship, if I double the distance between them, if I double the distance between them, then the new force of gravity will have to be 1/4. Right? So the two objects are further apart, therefore the force of gravity is going to be less, but it's not going to be twice. If I double the distance, it's not going to be twice as less or half. It's going to be 1/4 because of this squared relationship. All right. By that same token, if I move, let's say I have two objects and there's a certain force of gravity between them, and then I move it so there's only half the distance between them, then I would have to replace this with 1/2, and I would square it, and I would get this. And once I simplify this, I get 4. In other words, if I move two objects so they're twice as close, the gravitational force between them will be 4 times greater. Okay, so now we should be able to do example number 1. So those are our two relationships. Directly proportional to the product of the masses. Oops. Inversely proportional to the radius squared, or the distance squared. Okay. Oh, and before we do that, I don't know if I discussed this in another video already. Let's skip it for now. Maybe we'll come back to it. The force of gravity between two objects is measured to be 1.5 times 10 to the negative 16. Determine the magnitude of the force if one of the masses is doubled. So we don't have a formula yet, but we do have a relationship, and we've done this already. We've said that the force of gravity is directly proportional to the product of the masses. So if I double this, so I just put a 2 there, so essentially its mass was 1, now its mass is 2. In order to keep this relationship even, I would have to double the force of gravity, and therefore I'm just going to multiply the force of gravity times 2, and I'm going to get 3.0 times 10 to the negative 16 newtons. B, if the radius is doubled, so we sort of alluded to this one earlier also. It's an inverse square relationship, so I'm doubling the radius, so I have to replace this radius with a 2, because it's 2 times greater, but then I also have to square it, and I get a quarter. And therefore, to keep this relationship even, the new force of gravity must be a quarter of what it once was. So I'm just going to go a quarter times 1.5 times 10 to the negative 16, and that's going to give me 3.8 times 10 to the negative 17, which makes sense. If I move two objects further apart, the gravitational force between them is going to be less. It's, in fact, it's going to be a quarter less in this specific case. Okay, now, we can put those two ideas together, but we wanted, I said Newton wanted an equation, not just the relationship. He wanted an equation. And to make this equation work, you need this. You need big G. Big G is the gravitational constant. And big G is simply, very simply, a number that will make the formula work for every mass in the universe. So it's not just a number like 4 or 5 or negative 7. It's a far more difficult number to calculate. And Newton went about trying to calculate that number. And what he did was he rearranged the formula, as you can see in your notes, to this one right here. Oops. Rearrange it to this formula here. And then to see if he could solve for big G being the gravitational constant of the universe. Right, and mass is easy to calculate in both cases. The distance between the two masses is easy to calculate, but the problem that he had was this. What is the force of gravity between those two objects? And that is not an easy thing to measure. So, for example, if I have an apple and a pear and I'm holding them in my hands, and I'm saying, what is the force of gravity between those two things? How do I measure it? And the answer is not obvious. It's not easy. You can't feel the pear being attracted to the apple, even though they are, because all masses are attracted to one another gravitationally. So this was a huge problem, and in fact, Newton was not able to calculate what big G was. But we'll forgive him for that because he did about 8 billion other super important things that have changed the way we think about science and physics and math. So who steps up to the plate? Well, it's Mr. Henry Cavendish, and it was about 100 years later, as you can see in your notes. So Newton couldn't figure it out. It took another 100 years of advances in science for somebody to come up with an idea. And at this point, you should stop the video. You should go onto YouTube. You should Google Henry Cavendish, and you should watch a video about his torsion balance. This is how Henry Cavendish solved the problem, or how he came up with the value G, big G, by just basically taking two huge metal spheres, putting two smaller spheres next to them, all hanging from threads, and then watching them twist. They would twist very slightly because of the gravitational forces between them, and you would measure the twisting force or the torque right here. Anyway, watch a video about that. It's very cool, very ingenious on his part. And Mr. Cavendish came up with this number here. This is the value for G. This is the number that makes that formula true for every mass in the entire universe. 6.67 times 10 to the negative 11 newtons times meters squared per kilogram squared. And just in case you're curious about the units, why the crazy units? It's because if I take this formula here, and I just write it in its units, I'm going to get newtons on this side. We don't know what the units for G are, but we know that mass is kilograms. The other mass is kilograms. Oops, what did I put kilograms down there? That should be radius squared. Crazy, man. Radius squared is meters squared. So what are the units for G? Well, the units for G, if I want to have, I've got newtons over here, so therefore I need to have newtons over here. So let's put newtons in that, in for G. But then I need to get rid of all the other stuff. I need to get rid of all the other stuff. So I'll put meters squared up here, which cancels out those. and I'll put kilograms squared down here, which cancels out those, and then I'm left with newtons equals newtons. So that's why the constant g, the gravitational constant, has such odd units. Okay, here we go. We are going to use the values that we know to determine the mass of the Earth. Ingenious way to calculate the mass of the Earth without having to actually put it on a giant weigh scale. And we're going to do it like this. We're going to say that, so here's the Earth, and here's a man or a woman or a small dog standing on the Earth, and there's a gravitational force pulling the person towards the middle of the Earth that we measure with mg. But that gravitational force must be equal to the gravitational force between the man and the Earth. Okay, so this is man, M-A-N, the mass of the man. This is the mass of the man, and this is the mass of the Earth. And you can see the mass of the man becomes irrelevant in this formula. It's on both sides of the equation in the numerator, so it cancels. And then we can solve this formula for the mass of the Earth, and we get little g over r squared divided by big G. And those are values that we know. We know acceleration due to gravity. We know the radius of the Earth, because it's on your formula sheet. Just put E, 6.37 E6 squared divided by the gravitational constant. And if you put all that into your calculator, you end up with 5.99 times 10 to the 24 kilograms, which is pretty close to the general accepted value of the mass of Earth, and the one that's on your formula sheet, and that would be 5.97 times 10 to the 24 kilograms. So that's how we measured the mass of the Earth. Okay, example number 3. I'd say this is a more practical application of it, but not really, because we're just trying to determine the gravitational force between a pickle and a sandwich. Right? Straightforward problem. Both masses are given. Both masses are given. Right? Just plug them into the formula. Make sure that you change the masses to kilograms. Make sure you change the radius to meters. Make sure you square that radius. Make sure you plug it into your calculator correctly, and you will end up with a value of 2.3 times 10 to the negative 9 newtons. So that's how much gravitational force there is attracting the pickle to the sandwich. Now, by looking at a number, you should clearly be able to see where, when I'm holding an apple and a pear, I can't feel them being attracted toward one another. Why not? Because the force of gravity of the Earth pulling them down, or the gravitational field of Earth pushing them down to Earth, is far greater. If I just take the pickle, if I say the force of gravity acting on the pickle is going to be mass times gravity, which would be 0.2 times 9.81. I'm going to get, I forgot what that was, 0.2 times 9.81 is essentially 2 newtons. So that is not a huge amount of force, but it is infinitely bigger than this force that's attracting the pickle to the sandwich. So the force of Earth pulling down on the pickle is much, much bigger than this force here. And that's why the pickle and the sandwich are not moving toward one another. Okay, now there's one more problem. We're going to do that in the next video, just because this video is getting very long. So we'll see you for that one.